The first thing that we need to be able to tell the difference on is a cation and an anion. So what is a cation? These are positively charged particles, and an anion is a negatively charged particle. Okay, on your periodic table, there's a big split between cations and anions. Cations, the positively charged particles, are always the metals. Okay, and anions are usually the nonmetals. Okay, so on your periodic table, there's a big split. So that means cations are usually found on what side of the periodic table? The left, right? The left. The cations are the metals, so they're the left. And they're by far a majority on the periodic table. More cations than anions. Okay, and I'll give you a periodic table with all the charges on it so you'll be able to see. But it follows some rules with charges too. So, cations and anions, we need to review that a little bit. Metals and nonmetals. So when we're talking about naming, we're going to talk about naming a chemical formula. Okay, and what a chemical formula is it tells us the relative number of atoms in a chemical compound. Okay, and when we say it's the relative number, do you remember what relative usually means? Like in perspective of or in proportion to. So if I have the formula for water, which we know is H2O, and if I have two of those molecules, does it become H4O2? No, right? The relative number would be 2 hydrogens to 1 oxygen, right? So that's the chemical formula for water. Just because we have two of them, that doesn't mean it automatically combines into this new double-sized compound, right? That means we just have two individual water molecules. So chemical formulas have a specific relative number of atoms per the other atom, right? It's a ratio that's decided, right? The law of definite proportions. So, knowing what we know about a chemical compound, let's look at your periodic table. And let's review what it means to have valence electrons, or what valence electrons mean in general. Okay, what does it mean to have valence electrons? Those are your outermost electrons. Okay? And do you know the rule on the periodic table that valence electrons follow? So group 1 has how many valence electrons? 1. Okay, group 1 has 1 valence electron. Okay, group 2 has 2 valence electrons. Okay, now we skip the transition metals because they're funky. Group 3 has 3 valence electrons. Ooh. Okay, 4, 5, 6, 7, and 8. Okay, this is why some people will name their groups 1, 2, and then skip all the way over to 3. Doesn't make really a big difference, but that's the number of valence electrons that you see. Those numbers also can correspond to the charges. Okay, so I'm going to give you a table called the periodic table of ions, which tells us the charge of our atoms. If there's extras in the back, just leave them there. I'll come grab them. Okay, this is something that you will need to use often, very, very often, so please don't lose this. And this is the same as your periodic table, you need to have it often. Okay, so take a look at your periodic table of ions. Elements on the left side of the periodic table tend to have what charges? Positive. Right? On the left side tends to have positive charges. On the right side tend to have what charges? Negatives. Okay. So let's distinguish how the valence electrons matches up with the charge. Okay, in group 1, we said how many valence electrons do they have usually? 1. So is it easier for them to gather 7 to fill their octet or to give away 1? And if they give away 1 electron, what does that make their charge? +1. Right? That's where this +1 comes from in group 1. Okay, see, all of the group 1 elements have a +1 charge. Okay, because they have 1 valence, it's easier for them to give it away than to take 7, right, than to have a -7 charge. So when they give that electron away, they are left with themselves a +1 charge. Does that make sense where those charges come from? So group 2 follows the same rule. Is it easier for them to give away 2 or to take 6? Give away 2. So that's why they're left with a +2 charge. The transition metals are weird. Okay, they don't follow those same rules. So those charges are given there for you, but you can kind of associate the same rules with that, right? If they've got a +2 charge, that means they'd probably want to give away 2 electrons. If you look over at group 7, okay, or 17, the halogens, what is their charge? -1. So they have 7 valence electrons. Would they rather give away 7 and give them a +7 charge or take 1? Take 1. So if they take on an extra electron, their charge would be -1. Right? That's where those charges come from. So all of these charges here are not elements that are in their ground state, right? These are elements that want to bond, right? These are social elements. Okay. Some of them, like carbon, silicon, the 4 group gets kind of sticky because isn't it just as easy to give away 4 than to take 4? Yeah, realistically it is, right? So those ones can kind of go either way. They can have a +4 or a -4. So some of them in there are a little bit sticky, but for the most part they follow what's on here. It's also it's also important to remember that these aren't the only charges that are possible. These are by far the most common. Okay, so I know you could give up more electrons than your valence, but it would leave you kind of unstable. So this is the most common charges. Okay. All right, very good. Let's look at some of these transition metals in the middle. What do you notice about some of those guys in the middle? They have 2 charges. That means they are pretty stable, giving up 2 electrons or giving up 3. Right, so they can do it both ways. So when you're writing elements with these 2 different charges, see how there's a Roman numeral right beside it? That Roman numeral indicates to you the charge of that ion. So a Roman numeral always tells us it's a positive, whatever that Roman numeral is. Okay, so for example, with iron +3 and iron 2. Okay, those are both listed there, and you see the Roman numeral next to it. So when you see a Roman numeral, that means that an element has the ability to have 2 charges, and this is the one you should use, right? The +3 is the one you should use. You don't include Roman numerals for elements that only have 1 charge, okay? No Roman numerals for elements with 1 charge, okay? So let's start some naming. We're going to start with something called monatomic ions. Oops. What do you think monatomic means? How many? 1, right? Monatomic ions, that means it's an ion with only 1 atom. Okay? And this is how you name a monatomic ion. It's an anion. If it's an anion, it ends in IDE. If it's a cation, its name doesn't change. So if you notice on your periodic table, all of your anions are labeled nitride or oxide, right? It's not oxygen or nitrogen. As soon as it takes on that negative charge, it now is a negative anion, right? It's an anion, so it takes on the name for an anion, which ends in IDE. Okay, so anytime we've got a negatively charged particle, it should end in IDE. Okay, a single element or a single atom that's negatively charged ends in IDE. So all of these on the right-hand side, right, are single elements that end in IDE. Okay, you see that hydrogen is bumped over on the right side too, called hydride? It's pretty uncommon, but it can happen. Okay, it can give away that proton, but it doesn't happen very often. Or it doesn't give away a proton, I'm sorry. It takes an extra electron, which doesn't happen very often. Okay, so it's possible, but not a whole lot. Okay? So monatomic ions are very easy to name. If I asked for the name of, right, what would you tell me? Chloride. That's it. Chloride. Okay? And realistically, when we have a -1 charge, I'm only going to write the minus. Right? If it's a 1 either way, we can leave off the 1. But if our charge is not 1, then we have to write that number. So here, this one would be called oxide. Good. This would be called magnesium, right? Not magnesiide, right? Still magnesium because it's a positively charged, it's a cation. So it gets to keep its name. Yep, for anything that's just a single like this. And then we're going to show how we combine them when we have more than one atom. And it basically follows the same rules, you just combine those two things. So we could have a compound that looks like this, MgO, and it'd be magnesium oxide. Right, you're just combining those two. Okay, but we'll get to that. Okay. After monatomic ions come polyatomic ions. What do you think polyatomic ions mean? Good, multiple, okay, or many. Poly means many. So these are ions with multiple atoms. And polyatomic ions have specific names, and you will have a job today of memorizing some polyatomic ions. Okay? So these are polyatomic ions, for an example, would be PO4 minus 3. Okay? And this one, for example, is called phosphate. Okay, so it doesn't really follow a rule in terms of putting these two things together. But polyatomic ions have specific names, and what we'll do is we'll take a polyatomic ion and we'll pair it with some cation to form a neutral compound. Okay, so these are just like anions, but they just have more than one atom. Okay, so later today I'll give you a list of polyatomic ions that you will need to memorize. Okay, they don't follow as specific rules with naming like regular compounds do. Okay, so polyatomic ions are multiple. Yep, so we could have phosphate, we could have phosphite, right? From 8 to ite means one less oxygen, right? These are all types of rules I'll teach you when we look at our polyatomic ions, but yeah, there's some rhythm that you can find within the polyatomic ions, but for the most part, it's just a memorization thing. Okay, and you can see polyatomic ions listed up on the top of your sheet. These are ones, the blacked out ones are ones that you're going to end up memorizing. The other ones are ones that you could use, that you don't have to memorize. Yeah, we're going to have quizzes over the polyatomic ions, so you'll spend quite a bit of time memorizing them. Okay, it will save you a lot of time in your chemistry career if you can memorize the polyatomic ions. Okay? If you can have them memorized, that way when I ask you a question in Chapter 9 about sodium phosphate, you don't have to look up what phosphate is and then find the charge and then do all these things, right? If you know that phosphate's -3, you can build your compound, then you can do convert, it just saves you a lot of time. So memorizing the polyatomic ions may seem necessary, but it's not, I promise. Okay? So now let's look at what happens when we put together multiple into a neutral compound, because that's our overall goal. Okay, we're going to talk about something called binary compounds. What do you think binary means? 2. Good. So these are compounds made of only 2 elements. Okay, and the difference between a compound and an ion is that compounds have to be neutrally charged, so must have a neutral charge. Okay, so an ion has a charge, and we're okay with that. Compounds have to have a 0 charge, right? Neutral means 0, so compounds have to have a neutral charge. Okay, so this is how it works. If I wanted to form a compound between magnesium and bromide, okay, what's the charge for magnesium? +2. And what's the charge for bromide? -1. So there's 2 ways that you can go about combining these. The answer will be the same. There's 2 ways you can go about thinking it. Okay? So if I know that magnesium is a +2 and bromine is a -1, how many of these bromines do I need to make a neutral? 2, right? If I need to have a neutral charge, and I know this is +2 and this is -1, right? I need to have 2 of those. So we would write like this, MgBr2. Okay, that gives us a neutral compound. Magnesium is +2, bromine is -1, so -1 times 2 is -2, plus +2 gives us 0. Right? Do we understand how those two come together? The second way is more of a quick, quick trade type thing. So the second way is kind of called I just call it the cross down method. So what you would do here is you would drop the charges, right? If this is a 1, I'm going to drop the charges. I'm going to crisscross these down, and that would leave me with Mg1Br2, right? And if there's a 1 subscript, what can we do? We just leave it out. So it would leave me with MgBr2. Okay, both of those things are the same, right? These compounds look the same. It's just a different way of thinking about it. Okay? I tend to fall more with this method of just thinking, excuse me, my positives and my negatives have to balance, right? So if I've got a +2 over here and a positive 2 over here, or a -2 over here, they balance automatically. Sometimes the charges get a little bit more complex, right? If we don't have a 1, it's a little bit more difficult to tell how many of those we need, but it's still possible. Okay? All right, let's try another one here. Let's try a combination between Al and O. Okay, so aluminum and oxide. What is aluminum's charge? +3. And oxygen or oxide's charge is -2. So here is a little more difficult to think about how they're going to balance, right? It's still possible, but it doesn't come quite as quickly because one of them's not a 1. Okay, so if I need them to balance, right, how many aluminums would I need? 2. Al2, and how many oxygens would I need? 3. Right, that would give us here a +6 and a -6. Okay, or you can just do the cross method, which means we drop the charge and we cross down. That would leave us with Al2O3. Okay, either work fine. If you do the cross method, you should still check yourself in terms of the charges to make sure you didn't mix something up. So we think, okay, aluminum's +3, and we have 2 of them. That gives us a +6. -2 times 3 gives us a -6. Okay, so you should still be checking yourselves in terms of the charges. Okay, so we've learned how to build compounds. Now this is naming them. So all we do with naming like this is we literally put the names together. Aluminum gets to keep its name because it's the positive. Oxide ends in IDE because it's the negative. That's it. This is called aluminum oxide. Okay, aluminum's the cation, so it gets to keep its name. Oxygen's the anion, it gets to go IDE because it's negatively charged. Questions here? Okay, do you want to try one on your own? Or with your partner? Okay, you can try with your partner. Okay, let's see. I want a combination between potassium and phosphorus, or phosphide, sorry. Potassium and phosphide. Potassium and phosphide. I want you to name that and give me the chemical formula and give me the name. Okay, so give me the correct chemical formula and give me the name. So you can always look here. This would tell you.
What about it? Why?
Well, phosphate is a polyatomic ion.
Testimony.
Just phosphorus by itself.
That's with my brain.
Okay, Lauren, why don't you tell me what you had? Oops. Potassium phosphide K3P. Perfect. Okay, something that you should know with binary compounds is that the cation always goes first. Always, 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 always. So it's always cation followed by anion. Okay, always the cation goes first. Okay, so when you're putting together a compound, it goes left to right on the periodic table. Okay? Anytime you're putting together a compound, it should go left to right on the periodic table. So when in doubt, put your left first, right? When you're in doubt of which one needs to go first, it should always be cation, then anion, or left to right. Okay? If we have two negatives, we still go left to right. Yep. That's what will happen in our polyatomic ion, and very, very 98% of the time it goes left to right. Okay? Okay. Give me a combination between sulfur and barium. Barium's in group 2. All right, Haley, why don't you tell me what you got? Raise your hand if you agree. Perfect. Barium has to go first because it's the cation. Sulfur goes second. Okay, or sulfide goes second because it's the anion. Barium is a +2 and sulfide is a -2. So there's no reason we need to leave them at 2 and 2. Okay, we just reduce those down to 1 and 1. Okay, so we can reduce these. So for compounds between a cation and anion, or a metal and a non-metal, okay, these are ones that we can reduce. Okay, so overall, I guess I should have told you this before we started. This is called ionic naming. Okay, ionic naming. So put this at the top of your stain because there's two methods that we'll use, ionic and covalent naming. And ionic naming is between a metal and a non-metal. Okay, so that's what we've been doing so far. One from the left side and one from the right side. So this naming so far has been all ionic naming. Sorry I didn't tell you that at first. Okay. But ionic naming is always between a metal and a non-metal. Okay. So I should have given you that at the very beginning, but I forgot. Okay, now let's take it from the name to the compound. So if I give you calcium arsenide, I want you to give me the chemical formula for calcium arsenide. Raise your hand if you agree. Perfect. Good job. Perfect. Okay, calcium is a +2. Arsenide is a -3. So to get those to cancel, right, we take +2 times 3, which gives us a -6. We take -3 times 2 to give us a -6, and those give us an overall neutral charge. Okay, so binary compounds in general have to have that neutral charge. Any questions with binary naming? Okay, that's where we're going to stop for today with practice. We will deal with Roman numerals next class, naming ones with Roman numerals, and we'll deal more with naming with polyatomic ions next class. But for right now, you need to make flashcards for the polyatomic ions, so I'm going to put them up on the board for you. On your flashcard, you need the name on one side, and then the formula and the charge on the other side. So I'll put those up here for you. Okay, remember, left side is the 1s, right side is the 2s. That just means that's when we're going to test over them. So the 1s is the first group you should memorize, the 2s is the second group you should memorize. Okay, doesn't have anything to do with our charges.